Hello, Professor. My name is Sun TINGWEI. Today, I am pleased to present my research on the topic Machine Learning-Based Prediction of Heart Disease Risk. The application of machine learning methods in cardiovascular health assessment is of revolutionary significance, which can multivariate data through algorithms, break through the limitations of traditional models in the integration of nonlinear relationships and multidimensional filters, and build a more accurate risk prediction system. It can significantly process multi-source data, such as clinical indicators and lifestyles, realize early screening of high-risk groups through integrated learning, provide data support of clinical intervention, and help the accurate allocation of public health resources. I will introduce it from the following 6 aspects: abstract, problem statement, objective, methodology, discussion, conclusion. The first is the background and summary. With the advancement of artificial intelligence and medical technology, mathematical modeling has become a powerful tool for disease prediction. Machine learning enables computers to learn from algorithms and large data sets, enabling early and accurate detection of diseases for timely intervention. My study specifically constructed and evaluated 6 machine learning models, including random forest, naive Bayes decision trees, logistic regression, XGBoost, and KNN, and found that random forest and naive Bayes achieved an impressive accuracy of 89.99%. Validating the potential of machine learning for risk assessment while highlighting areas for improvement. Then there is the problem statement. The core challenge is the limitation of traditional cardiovascular risk assessment methods, which often lack precision due to static statistical models. By leveraging the Chinese heart disease dataset, I aim to address this gap by building a data-driven model that can better capture the complexity of risk factors, from clinical indicators to lifestyle behaviors. Then introduce the research objectives. My research focuses on 4 key objectives. First, to compare the performance of multiple machine learning algorithms to determine the most effective method for predicting heart disease. Second, the data processing steps are optimized, including missing value processing, filter encoding, and auto detection to ensure data quality. Third, identify the key traits that have the greatest impact on heart disease risk, which can inform clinical priorities. Finally, provide powerful data-driven predictive models to support clinical decision-making and patient care. Below is the dataset and pre-processing. The Congo China dataset presents both opportunities and challenges. There are 28 filters ranging from socioeconomic factors such as age, blood pressure, and cholesterol levels to employment status, and I reduced bias by inputting missing values, coding categorical filters, and detecting outlier by statistical methods. Next is algorithms and evaluation. I chose a different set of algorithms to test different learning paradigms, decision trees for interpretability, logistic regression, learning modeling, naive Bayes, probability, random forest, ensemble learning, XGBoost, gradient boosting, and KNN, instance-based, to evaluate them we used accuracy, confusion matrix, and ROC-OQ curve, a measure that balances accuracy, recall, and overall classification reliability. Then there's the model performance. Surprisingly, while naive Bayes, random forest, and KNN had the highest accuracy, 89.99%, all models had RQ scores close to 0.5, a result that shows that their categorical discrimination was no better than random guesswork. This contradiction indicates potential problems, simple imbalance in the dataset, for example, healthier versus diseased cases, weak future correlation, or low data quality that prevents the model from learning effective discrimination rules. This is followed by a discussion of the results. Future importance analysis reveals interesting patterns. In the naive Bayes model, unemployment status, alcohol consumption, and moderate debt scores are the strongest positive predictors, highlighting the impact of socioeconomic and lifestyle factors. In contrast, random forest priority clinical indicators such as blood pressure, CVD risk scores, and age, emphasizing the need to balance these two types of features in future models. Limitation analysis. The ROC plot confirmed my concerns. All Q values were around 0.5 for all models, and the results reflected random assortment. This means that while accuracy metrics indicate success, the model struggles to distinguish between positive and negative conditions, a serious flaw in medical prediction. Possible reasons include category imbalance, lack of information characteristic, or noise data diluting the real risk signals. In conclusion, this study demonstrates the promise of machine learning in heart disease prediction, with random forest emerging as the best performer. This study enriches machine learning applications in the Chinese populations and addresses gaps in traditional statistical models. Going forward, I propose 3 key steps: improving model interpretability, for example, through sharp values, to enhance clinical trust, integrating multi-source data, for example, genetic or environmental factors to improve predictive power, and improving data quality. Simple balance to mitigate categorical bias. By addressing these issues, we can unlock the full potential of machine learning in cardiovascular care. My introduction is over. Thank you for listening.